So, good morning, students. So, today's topic that I would like to discuss with you is the defects in ionic solids. Okay. So, first, I would like to give a brief discussion about ideal solids or ideal crystal. What is this? Because if in a crystal lattice, every lattice point contains its respective points or ions or the constituent elements, then we can say that it's a perfect crystal. So starting an ideally perfect crystal is one which has the same unit cell and same lattice point throughout the crystal. Imperfection or defects means the deviation from these regular arrangements of the constituent particles. So there are two types of defects which are generally observed in the crystal, and these are stoichiometric defects and not non-stoichiometric defects. So first I'd like to discuss about the stoichiometric defects. So these are the point defects that do not disturb the overall stoichiometry of the solid. That means if a crystal is formed by a unit charge cations and unit charge anion, then from the respective lattice side, the equal number cations and anions should miss. Okay. So in the ionic crystal, two types of stoichiometric defects are observed, and these are known as the Schottky defects and the Frenkel defect. So the Schottky defects or Schottky defects is it is caused when an equal number of cations and anions are missing from their lattice side, and this type of defects are generally observed in highly ionic compound. Mind it, highly ionic compound. Okay, where the size of the cations and anions are nearly similar. That means there should not be any large difference between the size of the cations and anions. Okay. And the coordination number of the ions are generally higher. That means 6 8 means octahedral site or cubic site type of crystals. Within this we can find the Schottky defects. Due to these defects, the density of the crystal decreases, because we know that from the crystal, if the corresponding lattice site loses some equal number cations and anions, then the mass of the crystal should decreases, and we know that density equal to mass by volume, but volume remains same, so definitely the density of the crystal decreases. So this is the respective figure where I can demonstrate in a regular figure. Look, this is a singly charged cations, anion, cations, anion, cation, anion, and suddenly in the second row, one anion is missing from this side. And to make the electrical neutrality, equal number of cations in the next row is missing. That means this is just a demonstrative figure. Okay, so equal number of anions and cations are missing from their corresponding lattice site, and thus that decreases the mass of the crystals, and that definitely decreases the density of the crystal. Okay, but maintain the electrical neutrality, because there should not be any excess cations or excess anions. Okay, so example of this type of defects that show that crystal shows is NaCl, KCl, cesium chloride, silver bromide. At room temperature, there are approximately 106 Schottky defects per cc or semi-cube of the NaCl crystal. So next is the Frenkel defects. It is caused when the cations are missing from their lattice sites and occupy the interstitial site. That means suddenly one cation is missing, or the finite number of cations are missing from their respective lattice site and occupy the interstitial site. So this type of defects are generally observed where there is a large difference in size between the cations and anions, because if there should not be any difference, then a cation is very difficult for a cation to occupy the interstitial position. Okay, as we know that metal cations are usually smaller in size than than anions, so it is easier for a cation to fix to the interstitial position. And due to these defects, the density of the crystal remains same, because a cation should not leave the crystal, but it just change its position from the perfectly lattice point to some interstitial position. Okay, so due to these defects, the density of the crystal remains same, but the dielectric constant of the medium increases. And Frenkel defects are common in crystal where the coordination number are usually not so high, means 4 6. Okay, so this is the a common demonstrative figure where the cation is smaller in size than anions, and this is the first row. There should not be any missing, but the second row, suddenly a cation is just change its position from this lattice side to some interstitial position. Okay, and the example that these ionic solids are usually show these Frenkel defects are zinc sulfide, silver chloride, silver bromide, and silver iodide. And it may be noticed that silver bromide shows both type of Frenkel as well as the Schottky defects. And the next topic is the non-stoichiometric defects, and these defects are of two types. So non-stoichiometric defects can be broadly classified into two types. These are the metal excess defects and metal deficiency defects. So first I would like to discuss about the metal excess defects. So metal excess defects are due to the anionic vacancies. So it has been observed that if NaCl crystal is heated in sodium vapor, means in presence of sodium vapor, it acquires yellow in color. The chloride ions diffuse to the surface of the crystals and combine with a sodium plus ion to give the NaCl, and the vacant anionic site, means chloride ion first diffuses to the surface of these NaCl crystals, and the vapor of the sodium ion and the combine with the vapor of the sodium ions and forms the NaCl vapor, and the leaves at the left side of these anions is occupied by an unpaired electron. So the anionic sites which are occupied by the electrons are called F centers or color centers. Sometimes these F centers are called Farbe centers because this is a German word which means the color. And another example is excess lithium ion. If lithium chloride crystal is heated with excess lithium vapor, then it crystal becomes pink, and excess of potassium makes potassium chloride crystals violet in color. So this figure just clear your concept. So sodium chloride. In the next row, one chloride is missing from your respective lattice points, and this anionic site is occupied by an electron to maintain the electrical neutrality. Okay, and the second metal excess defects are also occur because of these metal excess defects due to the presence of the extra cation in the interstitial site. For example, on heating of zinc oxide crystals, it loses oxygens and turns yellow in color. The excess zinc 2 plus ion moves to the interstitial sites and the electrons to the neighboring interstitial site. Means when you heated zinc oxide crystals, this is the general observation, but because in the laboratory also we observe these things. When you heated zinc oxide crystals, it turns yellow. That means some oxygen is loses from its sites, and the remaining the excess zinc 2 plus ions occupy the interstitial site. And this is the equation where you say that after heating some certain fraction X is of the oxygen is missing from these sides, and this is the leave from this side as oxygen gas. This is the respective figure, plus minus, and one of these excess. So after losing oxygen atoms, the excess zinc 2 plus ions or cations can occupy the interstitial side, and to maintain the electrical neutrality, electrons will also occupy some interstitial position. In this way, the electrical neutrality is maintained. And the last topic is the metal deficiency defect. This type of defect is generally found in among the compounds of transition metals which can exhibit variable valency or more than one valency. For example, if in a crystal of iron oxide is heated, if one of the iron 2 plus ion is missing from its corresponding lattice side, then the deficiency of the two positive ion, because one Fe2 plus is missing from the lattice side, then suddenly there is a vacancy of two positive ions, is balanced by the conversion of the surroundings to iron 2 plus ion to iron 3 plus ions. If the surrounding 2 Fe2 plus ion is converted to Fe3 plus ion, then the deficiency of these 2 plus ion is compensated. So in this way, the crystal will make the electrical neutrality. So Fe2 plus O2 minus, Fe2 plus O2 minus, in this first row there is no problem. In the second row, suddenly one of the Fe2 plus is missing, and to maintain the electrical neutrality, this Fe2 plus is converted to Fe3 plus, and this Fe2 plus also converted to Fe3 plus. So in this way, they maintain the electrical neutrality.